Climate change and global warming. In this lesson, we're talking about climate change versus global warming. What's the difference between the two? Weather versus climate, air convection currents, Earth's climate system, the ozone layer, the greenhouse effect, greenhouse gases, greenhouse gas emissions, global warming and the carbon cycle, carbon sinks, the effects of global warming, and then historic climate change. Climate change versus global warming. A lot of people use climate change and global warming interchangeably when really they're two different things. Global warming refers to the long-term trend of a rising average global temperature, and climate change refers to the changes in global climate which result from the increasing global temperature. So global warming, as the name would suggest, refers to the actual warming of the planet getting warmer, and then climate change is a result from the global warming. So as the Earth warms up, our climate changes as a result. Weather versus climate. Again, two terms people often get mixed up. Weather is atmospheric conditions, including temperature, precipitation, wind, and humidity in a particular location over a short period of time, such as a day or a week. So if you flip on the weather network, you see the 7-day forecast, that's weather. Climate, on the other hand, is the average of the weather in a region over a long period of time. So for instance, in September, the average temperature in Orlando is 32 degrees Celsius, and the low is 23 degrees Celsius, and they get about 11 days of rain. October, November, December, similar. If you were to go somewhere else, you get a different climate entirely. Say if you went to the Arctic, your climate would be much colder. It would have a lower average temperature. Air convection currents. Large convection air currents occur over the world because cool air is more dense than warm air. Therefore, it's going to go down. These convection currents can greatly affect weather in a region. So in general, what it means is that warm air rises and cold air sinks, and that gets a movement of the air molecules. You're always going to have your warmer air going up. It's then going to cool down when it gets up top. So it's going to cool down up here because as the air molecules spread apart, they start to cool down, they lose their energy, and then they're going to fall down because they get cooler. So then they're going to sink. Then they're going to get warmed near the surface of the Earth, and they're going to come back up. So you're going to get this continual movement of air molecules. Air currents in large bodies of water. During the summer, large bodies of water absorb a lot of the heat energy. So a lot of heat is going to be stored inside the water molecules. So this causes two things. Number one, in the summer, it's going to be a little bit less hot. So it's going to be a little more temperate because a lot of that heat that would otherwise be landing on the land is going and being absorbed by the water. In the wintertime, that heat is going to be released, making the climate a little bit less cold during those winter months. Components of Earth's climate system. We're going to have three main components. We're going to have the atmosphere, which is our layers of gas, including the atmosphere is the ozone, which protects us from the harmful UV light. The hydrosphere, so that's going to be our water vapor, ice. They're going to absorb a lot of the sun's energy, and they're going to contribute to the water cycle. And then you have the lithosphere, which is the Earth's crust, or the land, and it's also going to absorb a lot of the sun's energy. So all three of these things are going to contribute to the climate we have on Earth. The atmosphere. So we can only survive in the troposphere, which is this section right there. Air in the troposphere is mostly nitrogen and oxygen, about 78 and 21% respectively, and then about 1% other gas, including things like argon, carbon dioxide, helium, hydrogen, and ozone. And you can see in this picture right here, this top haze area, that's going to be our atmosphere. It's going to be the layer of gases that you can see, but generally you can see from an angle when you can see a little bit more of the molecules all concentrated together. Now, as you go up in the atmosphere, you get to the stratosphere, which is where our weather balloons are. And again, we can't survive there. The air is too thin, it's too cold. Meteors are going to be in the mesosphere. Those colorful lights you see up north, those auroras, are going to be found in the thermosphere. And then we get to the exosphere, which is about 10,000 kilometers up. So ozone is actually O3. So if we say O3, that's ozone. So the ozone layer is located between the stratosphere and the troposphere. So it's going to be located right here. Its job is to protect us from the UV light from the sun. Ozone depletion is caused by human-made compounds called chlorofluorocarbons, or CFCs, and halogens. So as that ozone layer gets depleted, more of these harmful rays can make it to the surface. CFCs and halogens cause chemical reactions that break down ozone molecules, reducing ozone's ability to absorb ultraviolet light. Many CFCs and halogens have been widely used as refrigerants and repellents, but their manufacturing has thankfully been phased out due to the harmful effects. So unfortunately, we didn't really know about the harmful effects while we were using them. Once we figured it out, we did something about it, which is great. Because if you take a look at this series of pictures here, this is what NASA predicted would happen between 1974 and 2060 if CFCs had not been banned. So you can see back in 1974, ozone concentration is going to be red to orange to yellow, and then we'll get less ozone, we're going to get to our blue color. So you can see as we go from 74 to 94, you have a little bit less orange and red up in North America. As we go to 2009, you get even less, and then you can see all the way down to 2060, there's pretty much no ozone left. So what they're saying here is that if CFCs hadn't been banned, we would have decimated our ozone layer in less than 100 years. The greenhouse effect. So for a typical greenhouse, just a regular greenhouse you might have in your backyard, light is going to pass into the greenhouse through the glass. The plants inside absorb the light energy and emit infrared radiation, or heat, which can't pass through the glass. So you can see these red arrows here bouncing off the glass, they can't get out. As the infrared radiation bounces around, heat is created and warms the area inside. That's why you can walk into a greenhouse in the middle of winter and it not be very cold. This, of course, is required for certain plants to grow in winter climates. Now, the atmosphere surrounding Earth acts in a very similar way. Light passes through the atmosphere and is absorbed by living things that emit the heat as infrared radiation. The infrared radiation interacts with the greenhouse gases in the atmosphere, which reflect the heat back towards Earth. And you can see that here. So here are greenhouse gases. Our solar energy, our light's coming in. It's going to be absorbed and re-emitted as infrared radiation by the living things on Earth. Some of that infrared heat is going to be reflected back by our greenhouse gases, warming up Earth. Now, the greenhouse effect is important. It's not this evil thing that we need to get rid of. Without the greenhouse effect, it would be much colder on Earth. So the heat from the natural greenhouse effect warms Earth's atmosphere by about 33 degrees Celsius, which is huge. If there were no greenhouse effect, Earth's average temperature would be minus 19 degrees Celsius. That doesn't mean it would be negative 19 degrees Celsius everywhere. What it means is that the average temperature on Earth would be negative 19 degrees Celsius. This may have made it so that humans didn't evolve. It may have made it that if we did evolve, we were really stranded along the equator area where it would be warm enough for us to survive. But nevertheless, life would be very different without the greenhouse effect. Greenhouse gases. Any gas in the atmosphere that absorbs infrared radiation from the Earth and as a result contributes to the warming of the planet. Most of the air in the atmosphere is made of nitrogen, oxygen, like we talked about 78 and 21% respectively, and they do not absorb radiation. The greenhouse gases that we were talking about are in very low concentration. And it's their concentration which determines how much energy they can absorb. So as we increase the greenhouse gas concentration, we're going to increase their ability to absorb this radiation and heat our planet. As I said, they're very low in concentration, only make up about 1% of our atmosphere. They're produced naturally and by human activities. Greenhouse gases include water, CO2, CH4, N2O, CFCs, and a few other ones. Now, the biggest contributor is water vapor, H2O. Water vapor constitutes Earth's most significant greenhouse gas, making about 95% of the greenhouse effect. Now, human activities do not release significant amounts of water vapor into the atmosphere, so you could say that we don't directly contribute to the amount of water in the atmosphere. Although we don't contribute directly to the amount of water vapor in the air, we do have a large indirect effect on it. So if you recall, warm air has a greater ability to hold water. That's why in the summer, it can be a lot more humid than in the winter when it's a lot drier. So by enhancing the greenhouse effect in other means, like pumping out CO2 into the atmosphere, we're increasing the overall temperature of the air and therefore increasing its ability to hold water. As we increase the temperature of the air, we're going to increase the amount of water vapor that can be trapped, and as we increase the amount of water vapor, we're going to further enhance the greenhouse effect and contribute to global warming. So let's talk about the other greenhouse gases. So out of the remaining 5%, 82% of that is carbon dioxide, and that's going to be released when fossil fuels, so coal, oil, natural gas, are burned. It increases due to the removal. It also increases due to the removal and burning of forests, industrial processes such as the manufacturing of cement, and the cultivation of soil. 10% is going to be methane, which is emitted during the production and transportation of coal, natural gas, and oil. Methane emissions also result from livestock and other agricultural practices. Nitrous oxide, it's produced when wood and fossil fuels are burned. It's produced by chemical industry and released by bacteria from fertilizers, and it traps heat 296 times better than carbon dioxide. So even though there's less of nitrous oxide, it makes a significant contribution to the greenhouse effect, much more than we give it credit for. And then we also have fluorinated gases, which make about 3% of the remaining amount. They're emitted from a variety of industrial processes, and they include things like hydrofluorocarbons, perfluorocarbons, sulfur hexafluoride, and nitrogen trifluoride. Global warming and the carbon cycle. So there are multiple contributing factors, but the consensus among scientists is that an increase in carbon dioxide is directly responsible for global warming. And by burning fossil fuels, people add about 5.5 gigatons per year into the atmosphere. And we're going to do that through the carbon cycle. And you can see that number right there. The 5.5, that's the amount of gigatons that we're releasing via fossil fuel burning. Things like industry, cars, heating homes, stuff like that. We're contributing a significant amount to the atmosphere. Now this graph is interesting because it compares carbon dioxide and temperature since 1880. So global temperature is going to be the bar graphs. You got the blue over here, and you got the red up there. And you can see a general upward trend as we go from 1880 to present day. But what you also notice is a gradual upward trend of the carbon dioxide concentration in the atmosphere. So you can see that there's a direct connection between the amount of carbon dioxide in the air and the average global temperature. But where is all this carbon? Like, are we just pumping it all out? Are we getting it from somewhere else? What are we doing to create all this carbon? Well, a carbon sink is a natural reservoir that stores carbon-containing compounds accumulated over a period of time. The main natural carbon sinks include oceans, so where carbon is dissolved, and organic matter. So living things are mostly composed of carbon-based molecules. So how do we affect these carbon sinks? Well, we're going to alter the carbon cycle, releasing carbon into the atmosphere faster than would normally occur, and that's going to be by burning fossil fuels and wood, and by clearing away vegetation, cutting down forests. This vegetation you can see here contributes significantly to bringing in carbon dioxide from the atmosphere into living things. So as we do this, as we change the way that the carbon is moved around the carbon cycle, we're going to change the concentrations. Something else that's not listed here is that as the temperature goes up, our oceans are going to start evaporating more. So this number right here, this 92, is going to go up. As we increase the air temperature, we're going to get more evaporation out of the oceans, which is going to send more carbon into the atmosphere. And this leads us to the carbon dioxide positive feedback loop. So what a positive feedback loop is that the previous thing causes the next thing to happen more aggressively or in a greater amount. So let's take a look what this is. So carbon dioxide traps thermal energy via the greenhouse effect. So we talked about that. The greenhouse gas carbon dioxide traps heat energy in the atmosphere. This increases global temperature. As global temperature increases, we get more carbon dioxide being released from our carbon sinks, like I talked about the evaporation of the water from the oceans. That's a good example. So as we increase global temperature, we get more carbon being released from the oceans. What that does is that it traps more thermal energy in the atmosphere because there's more carbon dioxide. As there's more carbon dioxide in the atmosphere, we get an increase in global temperature. As we get an increase in global temperature, we're going to further enhance the next step, which is carbon being evaporated from the oceans. So you can see how the previous step is going to contribute to the following step, and it's going to enhance it. It's going to make it bigger. So positive feedback loops can get out of hand because what they're simply doing is amplifying the process. So oceans are large carbon sinks, and as the temperature increases, more ocean water evaporates, releasing the carbon into the atmosphere, which further enhances the temperature, which further increases the temperature, as we just talked about. So again, just taking a look at our graph, we can see an increase in temperature and an increase in carbon dioxide are directly connected to each other. So what I'd like you to do is pause the video and take a look at number 6. Why should we care about a rise in global temperature? Well, the impacts of climate change are predicted to be serious and widespread, including things like more violent weather. Increases in global temperature will lead to melting glaciers, increases in sea levels, and flooding. Places like Miami will be underwater very quickly if the seas start to rise. Ecosystems will start to create unsuitable habitats. So think about polar bears and melting ice. If we remove the ice, then there's nowhere for the polar bears to be in the Arctic. So we're going to disrupt their ecosystem. And we're going to get shifting patterns of rainfall and drought. So even though it's global warming, we could get more rain in certain areas or less rain in certain areas. Places like Australia are significantly impacted by drought because they don't get a lot of rainfall. If the climate changes significantly, they might get even less rainfall. Places like California, greatly affected by wildfires, don't get a lot of rain. If the amount of rain that they get were to be reduced even further, then the wildfires would be even more extreme. And there's also the human health aspect. So this is from UC Davis. Worldwide increases in the incidences of asthma, allergies, infectious, and cardiovascular diseases will result from a variety of impacts of global climate change, including rising temperatures, worsening ozone levels in urban areas, and expansions of the ranges of communicable diseases as the planet heats up. So maybe you're not so worried about the polar bears and their ice sheets, but you got to keep in mind climate change will impact you specifically as an individual as well. Now, we do need to take a step back and think, has climate change happened before? So yes, it has. So take a look at this graph. It goes back about 400,000 years, and you can see that our temperature has fluctuated greatly over that time. In fact, about every 100,000 years or so, we see this spike in temperature, and then we see this drop in temperature. What we're noticing on the far right-hand side, however, is that our spike isn't really followed by a significant decrease. As you can see, this spike here, and then goes straight down. This one goes up and straight down, etc. We're not going straight up and straight down. We're kind of going up and to the right, which is very worrisome because we're not quite sure where that's going to go. Corresponding carbon dioxide graph on the bottom. You can see that all our peaks are directly connected to peaks in carbon dioxide, followed by decrease in carbon dioxide. But we're at a point where we don't really know where we are. Are those carbon dioxide levels going to keep going up? Are we going to see something like that? In which case, are we going to see a spike in temperature like that? We're not really sure, and that's very concerning. Historical climate change. We use climate proxies to piece together historical climate data. Climate proxies are preserved physical characteristics of the past that enable scientists to reconstruct historical climate conditions. Things like pollen records, ice core samples, marine coral, fossils, tree rings. These are all things that give us a good indication of what the climate was like in the past. Specifically with our ice core samples, ice is going to freeze in sections. So year 1 is going to be here. Then we're going to get ice on top of it. So we're going to get a layer there. Then we're going to get ice here, and so on, until we have many, many layers formed over thousands and thousands of years. Now, what makes up that ice is going to generally be H2O, but you're going to get different amounts of carbon dioxide being dissolved as well. So what we might see is more carbon dioxide in section 10 of the ice core, maybe this section here, closer to the surface. So this might be the last 100 years, let's just say, and much less carbon dioxide in previous years. So maybe 50,000 years ago, we have less carbon dioxide than we do today. And we can figure that out just by looking at the compounds inside those sections of ice. So sticking with my drawing, just to finish this off, this would be the past. So this would be 50,000 years ago, and this would be present day, or at least within the last 50 years. So what can you do about climate change? What can you do to combat climate change? What I'd like you to do is pause the video and make a list of at least 5 to 10 things that you could do personally to help combat climate change. So here's a list that I came up with for myself. Choosing reusable products. So choosing things like metal coffee containers instead of our disposable cups. Using less heat and air conditioning. So for instance, in the summer where I live, it can get up to about 30 degrees Celsius, and in the winter it gets down to about minus 20 degrees Celsius. So what we typically do in our house is we generally keep it around 20 degrees Celsius. But maybe in the summer, we could turn it down so that the AC is only on a little bit, and maybe, we leave it at about 23 degrees Celsius. And then in the wintertime, instead of bringing it all the way up to 20, maybe we let it go to about 18 degrees Celsius. So what we're going to be doing is using a little bit less heat and air conditioning in our home, buying energy efficient products, light bulbs, huge component, guys. You can save a ton of money and energy by buying these compact fluorescent light bulbs, much more energy efficient than the traditional incandescent bulb, driving less, so biking, walking, turning lights off, buying local products, planting a tree, all these things can make a big difference in your community. And that concludes the lesson on climate change.